In fact, quantum mechanics almost could not be more obvious, at least to those of us fortunate enough to have colour vision. Look at some object, such as these toy bricks here, these nice blue toy bricks, or possibly this tennis ball that I have here. It's a kind of glaring fluorescent yellow. Now, we could say that each of these contains some appropriately coloured pigment, a dye or something, based on some material with an intrinsic colour. But that's not much of a theory. We're really not much further forward in our understanding of why these things are the colour that they are. And if we don't know that, then we could be stuck in medieval times, where artists had to find nearly all their pigments in the colours in natural objects, sometimes at very great cost. This is a painting here by the Italian Renaissance artist Raphael. It's from 1503, and it's known as the Diotalevi Madonna. Now, if a painting at that time had this particularly rich, deep blue, as you see in the cloak here, you would know it was very expensive. Good blue pigment was hard to come by, and typically a blue like this at that time would be what is known as an ultramarine blue, which quite literally means that it had to come from across the sea, ultramarine. There are actually relatively few naturally occurring materials that are a deep blue and that are suitable for use in paints. Ultramarine blue is made from a semi-precious stone called lapis lazuli, and that name means stone from Lasward, which was a place that the stone was originally mined. In Raphael's time, the lapis lazuli probably came from Afghanistan, where it has actually been mined for over 4,000 years. The words for blue in French, azur, Italian, azzurro, and Spanish, azul or azul, and I apologize for my pronunciations there, all come from this same root, the word lazuli. The fact that all these languages adopted the same word for blue shows how unusual a colour this is in the natural materials that we have available to us, and indirectly, how little ability we had to make materials of a given colour. Part of the difficulty there is that there's no classical theory that explains why materials have the colours that they have. It's really a complete mystery in classical physics, and as a result, something over which we had very little control. Now, modern blue colouring, like you see in these bricks here, is probably made from a man-made material. A very common one is copper phthalocyanine, and that's a material that was discovered actually by accident in the 1930s as a very good blue colour by a chemist. And as a result of our modern understanding of chemistry, which to a large extent is based in its microscopic science on quantum mechanics, we understand how to make materials of the colours that we want. And as I say, we can make those nice blue bricks, or we can even make colours that don't exist in nature, like the fluorescent yellow of this tennis ball here. Actually, it was a related problem of colour that got us started in quantum mechanics. Of course, people had known for a long time that hot objects give off light. So a fire or a candle flame are good examples. And for many years, these were the main kinds of sources of light that we had in the evening. Blacksmiths also knew empirically how to gauge the temperature of materials like iron, based on how it glows when it's hot. And in the latter 2 decades of the 19th century, electric lighting was becoming increasingly popular, especially after the successful invention of relatively long-lasting so-called incandescent light bulbs, the electric bulbs that we've known for many years. And incandescent here simply means that something is glowing because it's hot. Now, with care and operation at low power, such bulbs can actually last a very long time. This carbon filament bulb that you see here is in a fire station in Livermore, California, and it has apparently been running for 110 years. However, a key problem with such filament light bulbs is that they are not very efficient at converting the electric power into light power. And depending a little bit on the detail of how we define efficiency, that conversion is only a few percent. Hence, it became rather important to understand just how efficient such light bulbs could be. Now, the history of that and what happened in understanding efficiency of light bulbs is something that took place largely in the latter years of the 19th century, and it's a particularly interesting interaction between science and engineering. In 1887, the German government, stimulated in part by Werner von Siemens, the inventor of the dynamo, and you may have heard of the Siemens company, which still exists today, the German government founded the Physikalisch-Technische Reichsanstalt, or PTR, the Imperial Institute of Physics and Technology near Berlin. And over the next decade or so, this became a very well-equipped research facility. One of its priorities was to understand exactly this question, the light emission from hot bodies, with a goal of understanding how to make better light bulbs. Now, it was already understood by this time that if you made something that perfectly absorbed light, then you heated it up, it would become the best possible emitter of such thermal radiation. This is known as Kirchhoff's law of thermal radiation. And there's a bit of an irony here in the terminology, but because that best possible emitter is therefore the best absorber of light, it's called a black body. So our best possible emitters are called black body emitters. Now, at this institute, by the late 1890s, quite precise measurements could be made of this so-called black body spectrum, the different colors that came off as you heated bodies up to different temperatures. And the problem about this was explaining why this black body spectrum had the shape. So we see here an example of a black body emission spectrum, which shows the amount of light emitted as a function of the wavelength. This spectrum is for a body at 5,800 degrees Kelvin, which is approximately the temperature of the sun. In fact, at the sun's surface, before the sunlight has been somewhat filtered by absorption and scattering in the Earth's atmosphere, that is pretty much what the sun's emission spectrum would look like. A cooler body at 3,000 degrees Kelvin has a similar shape, but it emits much less light, and its peak emission is shifted to longer wavelengths. And to see the challenges, incidentally, for practical light bulbs, we can look in more detail at these spectra in the visible range. And up the top here, we've added in an approximate representation the color of all of the different wavelengths, and they're in the visible spectrum there. We can see that the power of the sun is relatively uniform per unit wavelength across the visible spectrum. But if we look at our 3,000 degree Kelvin light bulb filament, first of all, it's much, much weaker, about 25 times weaker, and also it's not such a nice distribution of colors across the visible spectrum. So let's go back to our black body spectrum at 5,800 degrees Kelvin for a moment. The key question is, why is it this shape? Which is the same thing as saying, why is it this color when you heat something up? Now, the model that followed from the best understanding of classical physics at that time was called the Rayleigh-Jeans model. And first of all, at the longer wavelengths over towards the right here, it somewhat overestimated the black body emission. But more importantly, at short wavelengths, it predicted that the amount of radiated power would keep on increasing. And empirical measurements just did not agree with that. It would also have created more basic problems theoretically because it would predict an unlimited amount of power could be radiated by a warm body at short wavelengths. Hence, this difficulty was called the ultraviolet catastrophe. So we certainly need another model for the shape, and it needed some new assumptions. Wilhelm Wien, working at the PTR Institute, had come up with some important relations, one of which, his displacement law, so-called, has stood the test of time. We still use that today. Another formula he had for the shape of the spectrum initially seemed to be working, but eventually it became clear it simply did not work at long wavelengths. Max Planck, who was then a professor at Berlin University, in fact he had taken over Kirchhoff's former position there, was quite aware of all of this work, and he had a particularly strong background in the necessary thermal physics, and he worked hard on this problem. He came up basically empirically, not based on any fundamental physics, with a mathematical formula, and this was October 1900. And this formula fit all of the experimental data very well. But as I said, he actually had no physical model as to where this came from. He continued working in this problem, and just before the end of 1900, on December the 14th, he presented his proposal at the Physical Society in Berlin. And this proposal is now regarded as the start of quantum mechanics. Planck made one key assumption. He said, let's just presume, for some reason we don't know, that light is emitted in chunks, or quanta, as he called them, of an amount proportional to the frequency of light. So we get this formula, E equals h times nu. In the way this is usually written, the Greek letter nu stands for the frequency in hertz, which means cycles per second, of the light. Now, it was already very well understood at that time that light was an electromagnetic wave. That's just like radio waves, for example, are electromagnetic waves. Although the frequency of light is very much higher. It's about 10 to the power 15 hertz. And that's much larger than we find in radio waves. But still, we believed, and we do believe today, of course, that light is electromagnetic waves. The proportionality constant h that he chose is known as Planck's constant. And that's simply a number that he chose so that he could get his calculated blackbody emission spectrum to agree with the measurement. This constant is about 6.626 times 10 to the power minus 34 in units of joules, the unit of energy, times seconds, the unit of time. And the value we are showing here is the best accepted value as set in 2010. Now, an important point here is that when Planck was proposing these quanta of emission, he was not actually proposing that light existed only in such quanta. That would have caused quite a conflict with what people then understood about light, that we had this extremely successful theory of electromagnetism, and that theory had light as waves, not particles. And this was an old battle. Back in the 1600s, the late 1600s, Isaac Newton, the very famous inventor of classical mechanics, had done a lot of work on light. In fact, he did some very good work on light. And his idea was that light was made out of what he called corpuscles, little particles, essentially. And he said this because he said, well, sound is waves because sound can go around corners, but light doesn't go around corners. You can't see somebody around a corner. So he said, I think light is made up out of particles that go in straight lines. So that was Newton's idea. But then at the same time, Christian Huygens, working in what is now Holland in the late 1600s, had apparently been won over quite convincingly by the idea that these were actually waves. He had a very good theory of waves. It wasn't quite dead right, but it was actually a pretty good theory of wave propagation. And it wasn't until the early 1800s that this controversy between the corpuscular model of Newton and the wave model of Huygens really became resolved. There were some profound experiments, one of which we will get back to later on, called Young's slits, that show rather convincingly that light is actually made up out of waves. And at this time in the late 1890s and on into the early 1900s, of course, we already had available to us the extremely successful and deep theory of electromagnetism from James Clerk Maxwell, working in Britain or Scotland. And he had constructed what are known as Maxwell's equations, which are one of the major triumphs of 19th century physics and underlie everything that we do with electromagnetic waves today. So that theory was very strong. It showed light as waves. There's no doubt about that. So Planck was not proposing that somehow light only existed as corpuscles or particles. He was saying light is waves, but for some reason in these so-called black bodies, it's emitted in chunks. There was, however, another set of odd observations, first made by Heinrich Hertz, the same man whose name is on the cycles per second, in 1887, that if you took some metal plates, put a voltage between them, and then shone ultraviolet light on one of them, the spark between the plates became brighter. Now, the light that he shone on these pieces of metal had to be ultraviolet light, and he knew this in this particular set of metals. It had to be ultraviolet, because if he put in a glass plate in front of the light, this additional sort of sparking effect stopped. Various people looked at this phenomenon after that, and Hertz himself sort of moved on, and it remained a puzzle for many years. Now, in 1902, Philipp Lenard, who had been Hertz's assistant, continued these experiments and was able to clarify that there was a flow of negative charge between the plates if we had them in a vacuum when we shone light on them. And by biasing the plates with a voltage to stop the current, he was able to deduce how much kinetic energy the negative charges had when they left the plate. That is, if these charges come off the plate with some amount of kinetic energy, that would allow them to keep on moving, and some of them would be moving exactly towards the collecting plate here. And to stop those and stop them getting to the collecting plate, we would have to somehow put enough force on them from the electric voltage applied across here to just stop them from getting there. Now, the surprise here is that with an obvious classical way of looking at this effect, we might think that shining a brighter light on the plate would lead to electrons with more kinetic energy. And so they would be harder to stop. And so we'd have to put more voltage on the plates to sort of stop them from getting there, more repelling force on them to stop them from getting to our collecting plate on the right here. For example, if we were heating the plate up with the light, we might expect that with a brighter light, the electrons would naturally be hotter and they would have more kinetic energy just because there was more power in the light beam. But this is not what happens. Instead, when we shine the light, yeah, we get more electrons off, but the stopping voltage remains the same. That is, the electrons always seem to be emitted with the same kinetic energy. And furthermore, if we change to a shorter wavelength, say moving from blue or ultraviolet further into the ultraviolet, then we have to increase the stopping voltage to stop the flow of current. With shorter wavelengths, the kinetic energy of the electrons was greater, and it didn't matter how bright the light was. We still needed the same stopping voltage to stop the electrons managing to get to the collecting plate, no matter how bright we turned up the bulb. In 1905, Einstein made a proposal to explain this strange effect. He said, light is actually made up out of particles. And these particles, we're going to call them photons, and we will say that they actually have energy h nu. So this is the same formula that Planck had, but here we're actually saying light really is made up out of these particles that have this energy h nu. So this is a step beyond Planck, who, as I said, was only proposing light was emitted in these chunks, but he wasn't trying to leave behind the wave theory of electromagnetism and substitute a corpuscular one. So the explanation of the photoelectric effect is as shown in this diagram. We presume that electrons in a metal sit in some sort of pool, and there is an energy barrier called the work function, here the Greek letter phi, and the electrons have to overcome this work function to get out of the metal. So a photon with energy h nu that exceeds the height of the barrier, exceeds this work function phi, will have enough energy to allow the electron to be extracted from the metal, and the excess energy the electron gets from the photon will be given to the electron as kinetic energy. In the worst case, as I said before, all of that kinetic energy will correspond to motion in the direction towards the other electrode, and we will need the full stopping voltage to slow that electron down to zero velocity so it never quite gets to the other electrode. It was this proposal, which explained the photoelectric measurements of Leonard so well, that led to Einstein's Nobel Prize, by the way. He got his Nobel Prize for his proposal of the photon, not for his proposals about relativity. And so we come to something we call wave-particle duality. We're saying here that light is displaying both wave character, and it certainly does do that, and is also made of particles. But how can this be? How can light simultaneously be a wave and be a particle? That simply does not seem to make any sense to us in our classical view of particles and waves, and it certainly did not make sense to Planck. Now, strangely enough, in the end, once we've constructed our quantum mechanical theories, this wave-particle duality is actually not a problem within quantum mechanics. However, the key thing we have to do is we have to avoid bringing everything along from our classical ideas of what we think a particle is, and everything that we think of a wave in the classical world as having as its properties. We can only bring some of those properties. That's how we get rid of the contradiction. And we will see how we do that later on, but we need to do some more quantum mechanics before we can get there. And incidentally, in case we were in any doubt about wave-particle duality, we can note that we can verify it literally trillions of times a day. Modern telecommunications that we use for the internet is carried over optical fibers. They carry essentially all of our long-distance information on the internet. When we design the optical fibers themselves, or hair-thin pieces of glass, they're designed by considering light as waves, the electromagnetic waves of Maxwell's equations and 19th century physics. And the devices that generate the light beams that go down the fibers are lasers, and the devices that detect them at the other end are photodetectors. Both those lasers and photodetectors are fully quantum mechanical devices. They generate photons and they detect photons. And since we send trillions of bits per second over the internet every day, we are actually verifying the photoelectric effect and this quantum mechanical description and the wave-particle duality all those times every day. So now we're beginning to see quantum mechanics take shape as it starts to explain aspects of light that we could not understand before, even if it's introducing some ideas like wave-particle duality that seem very bizarre. And indeed, even though Einstein got the Nobel Prize for his explanation of the photoelectric effect, it was at that time by no means clear to physicists that this actually made sense. Incidentally, it's amusing to think that that light bulb I showed you that is burning in Livermore, California, has actually been burning since it's been burning for over 110 years, since before Einstein proposed the photon. Having studied quantum mechanics with light, for the next chapter in this story, we will be moving on to the early history of the quantum mechanics of matter. How do we understand materials and their properties?